again, Business Analytics students. In this second video for lesson 3-2, we're going to learn how to conduct a chi-square test in Excel. Step 0 was to identify if the test was appropriate. We did that in the last video. In this video, we're going to discuss steps 1 to 4 for conducting the test. Step 1 is to write the hypotheses for the chi-square test. The chi-square test is designed to compare the counts of two things: the observed distribution, which are the counts that you actually get from real data, to the expected distribution. This is the null that you would get given to you in the question based on a theory or model or just equality of all the groups. The way that we write them is in text and not using symbols, so you don't have to use symbols like you did for the t-test. You'll use more of a text-based approach like we did for the alternative of ANOVA. The null will be written that the two variables are independent, or that the observed counts and expected counts would be about equal. Whereas the alternative you're trying to prove is that the two categorical variables are dependent. This means that the observed counts are not the same as the expected count, and there's some kind of pattern in the counts to say that like one group is higher than another group, for example. You'll always be able to write the null and alternative in this way. However, you can specify what the categorical variables are. So instead of just writing two categorical variables, every time I ask you to write the null and alternative, you should say what the null and what the two categorical variables are for that null and alternative. For step 2, you need to write out your conditions. So the counted data condition is that the data must be counts from a categorical variable. Otherwise, the chi-square test is not appropriate. If you don't have counts and you have something that's quantitative, then you should probably be doing a t-test or ANOVA. So you need to make sure that condition is met before you proceed. Then, just like for ANOVA or t-tests, chi-square tests require both independence and randomization. When we talk about independence, we mean that the counts in the cells should be independent of each other. And for the randomization condition, that the individuals, or it could be items, depending on what you're talking about in the question, should be from a random sample. Finally, the expected values should be at least 5 in each cell. When we talk about the expected values, we mean the expected model values, not the observed distribution you actually get from the random sample. So the expected values are something that you typically have to calculate, and those should be at least 5 per cell. Once you've checked the conditions, if all of these are met, then that means the chi-square test is an appropriate type of test to use, so you can proceed to the calculations. For the calculations, first you need a table that actually gives you the observed counts from your data. That's what we would call the observed distribution. Usually you make that in Excel yourself by either constructing the table using counts, or you're given a table, or the fastest way is often to use the pivot table. Then, once you have a pivot table of the observed values, you can calculate the expected values from the model. If you have just a single data group, you can use that the expected frequency is the sum of the observations divided by the number of observations. But if you have multiple groups, then you'll need to use the formula that you have a row total times column total over table total. This is basically just like a weighted average of values based on their position in the table. I'll explain how this works when we look at an example. Once you have the observed distribution from the data and you've calculated the expected distribution using one of these formulas, then you can calculate the chi-square test statistic. The chi-square test statistic is calculated by adding together for all cells the observed value minus the expected value squared, then dividing by the expected value. The reason that this is called the chi-square test is that this uses what's called the chi-square distribution. So far, from statistics into business analytics, you've learned the normal distribution, the t-distribution, and the f-distribution. The chi-square distribution is just another type of distribution. Like the f-distribution, it is skewed. If you look at these pictures here, they show two different chi-square distributions. one for 5 and one for 9 degrees of freedom. And they are both skewed distributions, which means they are not symmetric. If you folded them in half across the highest point, the peak in the middle, that mode, the two halves would not match up. Because the distribution is skewed, that makes the chi-square test a one-sided test. Also, the chi-square distribution is like the t distribution and the f distribution. It does change shape as the degrees of freedom change. That's why this picture shows two different examples, one with 5 and one with 9 degrees of freedom. You can see the one with 9 degrees of freedom is kind of a bit more flat. It slopes out more gradually, and that would be true as you keep increasing the degrees of freedom. When we talk about the chi-square test for a table, so if you've put your counts into a pivot table or a table, the degrees of freedom for the test would just be the number of rows minus 1 times the number of columns minus 1. So if you remember for the t distribution, the degrees of freedom were n minus 1. It's similar to that, just rows minus 1 times columns minus 1. Once you've calculated the chi-square statistic, for this chi-squared statistic, we can find a p-value from the chi-square distribution. Once you calculate the p-value, this p-value works like any other p-value in terms of the decision that you make. However, note that there's no tool in the data analysis tool pack for calculating the chi-square test statistic. If you look within the data analysis tool pack, you won't find anything there about the chi-square test. You just have to use the formulas that are listed here. The formula for the p-value in Excel is this one here, chi-square.test, where you select the actual observed values and the expected values that you calculated in step number 3. And then, as I mentioned, the p-value works the same as always. If it's less than alpha, you reject the null hypothesis. And if it's greater than or equal to alpha, you do not reject the null hypothesis. So the best way to learn about the chi-square test is to actually do an example. So we are going to do a chi-square test for the insurance survey data that was found in the Learning Outcome 3.4 sheet. Specifically, we want to see if there's patterns between gender and education level, college graduate, graduate degree, or some college. So step 1 would be to state the null and alternative hypotheses. We know the null hypothesis is always that the two categorical variables are independent. So all you need to do is rewrite that statement stating what the categorical variables are in this case. So I would write education levels for people on the insurance survey are independent of gender. So that's, as long as I have both the variables in there, education, gender, and independent, that's what you need in your null. The two variables and independent. For the alternative, you need the two variables and dependent. So I would have education levels for people on the insurance survey are dependent on their gender. And that's it. That would be your null and alternative. You can state them all in words. You don't need to use any symbols. After that, step 2 was to check the conditions and assumptions. First, is the data counted? In the previous example, we talked about how both female and male and the education level, college graduate, graduate degree, and some college, are both categorical variables. Because the variables are categorical, all we can do is count how many people fall in each of the categories. So this would be counted data. That condition is met. So for the independence condition, do you think that one person's gender and educational background will change another person's? If the sample is taken randomly, then one person should be independent of another. There's no reason to think that there should be a relationship between those demographic factors if the sample was actually random. For randomization, we don't have the whole background for how this survey collected the data. We don't have a lot of information on it. But surveys are supposed to use random samples, not other methods like convenience sampling, to be valid. So it should be a random sample if the survey was properly conducted, but this really isn't specified in the question. And finally, for the expected value, this is something we actually have to come back to because for the expected values, you have to calculate them. And that's what we're going to do next in step 3 for the calculations. So for the first step, you need to just have the observed counts. We already found them using the pivot table here, but I'm just going to copy paste the numbers only in here so that I start just my own little table from scratch. So I just copy pasted the numbers and I'm going to build my own formulas for the totals. I'll find the sum across the rows and the sum across the columns here. Once you have your table of observed values, the next step is to find the expected values. In this case, we have multiple groups. What I mean by that is we have male and female. That's 2 different category options. And college, graduate, and some college. That's 3 different category options. So because we have a table that's 2 by 3, that's what's considered multiple groups. 2 rows here, 3 columns. So we would need to use this formula. The expected frequencies will be each row total times the column total over the table total. So for female, for example, it would be the row total for females times the column total for college graduate, since that's the column I'm in, divided by the table total of 24. And I'd get 5.25. If you want to drag this formula to work, you'll see I get these div 0 errors because you can see that the formula is correctly moving for the red reference to the next column, but for the row total for female and for the table total, it moved incorrectly. So in order to get this formula fixed, what you need to do is lock some of your cell references. Particularly, if you want the row totals to stay as either 14 or 10, the totals of the 2 rows, those are both found in column E, so we need to lock in the E. If you want the column totals to stay as the 9, 8, or 7, those are all found in row 77, so we need to lock row 77. For the grand total of the table 24, that number should always be 24, never change, so I need to lock both the E and the 77. If you lock it just like that, and then you drag and fill your table, you should get the correct numbers. Notice that the insides of the table have some decimal values, but the outside totals stay the same. 9, 8, and 7 for the totals based on the columns, and 14 and 10 for the total genders based on the rows. But these are the expected, like weighted averages for each of the values. Now that we have the expected values, we can check the expected value condition, which says that each of these numbers should be bigger than 5. In this case, we actually only have one that's bigger than 5. All the rest violate the condition. So this sample is technically a bit too small. 5 out of 6 expected values are less than 5 when they're supposed to be greater than 5. All this means is you would really need a larger sample to get better results. So for this introductory example, we didn't want to use a huge data set, but really 24 is a bit too small to only ask 24 people to develop reliable conclusions. We see that in the expected values, that each one of these should be bigger than 5 to use it, but we're turning out a bit smaller than 5. We will still proceed with the test to show you the steps for it, but just know that you would want a larger sample than this in real life so that you get expected values all bigger than 5 instead of just the 1. Now that we have the original observed values from the data set, just the values from the pivot table we made based on the random survey, and we have the expected values we calculated based on the formula, the next formula is we need to calculate the chi-square statistic. The chi-square statistic is calculated by taking the observed values minus the expected values squared over the expected values. So for each of these individual cells, you would take the observed, like female, observed female college graduate minus the expected female college graduate and square it, and then divide by the expected answer. And then I'll just fill in the whole table. You can click on any of them and see if it worked correctly. It should always take observed minus expected in the same position, square it, and divide by the expected. And that's how you calculate the chi-square values. To get the chi-square test statistic, you just add them all together. And it's 2.83. The bigger this value is, the more likely you are to reject. But to actually make a real firm decision, you need the p-value. And for the p-value, we use this formula. Chi-square.test, select your observed values, select your expected values. So this one, chi-square.test, actual range is the observed. These ones here, don't select the totals though, just select the numbers inside the table. And for the expected value, same thing. Just select the numbers inside the table. That's actually the data values, not the totals that we found. The row total and column total were just needed for the expected value calculation. You don't need them for the p-value. And our p-value is 0.2426. We use the p-value like always. If the p-value is greater than alpha, you reject. Typically, we use our 0.05, 5% for alpha. 24% is definitely bigger than 5%. So our decision would be do not reject the null hypothesis, because we can only reject if we are smaller than the 5%. In this case, we're bigger than the 5%. I think I might have said that backwards at one time, but the 24% is definitely bigger than 5%, like I'd written out here. So because we're bigger, do not reject. You can only reject when you're smaller than the 5%. And finally, what does do not reject the null hypothesis means? Do not reject the null hypothesis means we're staying with the null, that education level and gender seem to be independent. That means that there's not really a significant difference in these counts in the table from what you would expect here, the expected values. So there's two ways we could really write this out. Education levels for people on the insurance survey are independent of gender. That means the counts in each cell are not significantly different. Is another way of wording that is you're not seeing big differences between like males getting more graduate degrees or females not finishing college as much. We're not seeing any patterns like that by saying education level and it is independent of gender. We're not seeing a strong relationship between the gender of the person and how much education they received. In general, for the calculation steps, first you'll make a table, usually a pivot table, that will find you the counts for the cross tabulation. Then you calculate the expected values. The safe formula to use for expected values is this one, because technically this first one for a single group, it's actually just this formula simplified. If you only have one row, for example, the formula will just reduce or simplify to this formula. So as long as you know this one, row total times column total over table total, That's the one that you need for the expected values. Then you use the chi-square test statistic that you do the observed minus expected squared over the expected values and add them all up. This gives me my individual values and I add them all up to get the total test statistic. And finally, for the p-value, there's a built-in function in Excel called chi-square.test where you take your actual values and your expected values, put them inside the function, and it calculates the p-value for you that we use to make our decision. It does take a bit of practice calculating the expected values and the chi-square values, so I do have a learning check question for you to try. In this one, it's about energy drinks. We have respondent number, gender, and their brand preference, all filled in here. What you want to do is look at the counts of brand purchases, brand 1, 2, or 3, by gender, male or female. I've set up spots for you to put the null and alternative hypothesis. To briefly check the conditions, you can summarize them in this box quickly here. A box for the chi-square test statistic result. Add them all together to get the test statistic, and then use your formula chi-square.test to get the p-value. From the p-value, you can make your final decisions. Please pause the video here, and then when you click play, I'll show you the answer. So I do want you to try the question here by yourself first to see if you can try the formulas out. And then when you press play again, I'll show you and explain how the formulas work to make sure you're getting the right answer. Okay, so I hope that you paused the video. I'm going to show you the answers now for the learning check question. What I did first here is I found the pivot table for female, male, and brand 1, 2, and 3. For my quick check of the conditions, I said that this definitely does represent counts because both brand and male and female are categorical. One person purchasing brand 1, 2, or 3 for energy drinks should not influence another's purchase if it actually is a random sample. And for a random survey, it should be randomized. And for the expected values, you'll have to actually calculate those, which I do below, and they all end up bigger than 5 this time. So this actually is a big enough survey because they ask 100 people that size condition for the expected values is not violated here. They're all bigger than 5. For the null and alternative, you have to have both variables in there somewhere. So instead of just saying the two variables are independent for the null, I have that brand preference for energy drink is independent of gender. And the alternative has to have both variable names independent. So I wrote brand preference for energy drinks depends on gender. For the expected values, what you have to do is take the row total times column total over grand total. So your formula should look like this. I've locked in the J for the row totals, the 10 for the column totals, and the J10 for the grand total of 100. And then I did that for every single cell, just dragged it across, and that gives me all my expected values. Notice that all of these numbers are bigger than 5. The smallest one is 8.51, so we've exceeded 5 and that condition's met. Then for the chi-square test, you have to take observed minus expected squared divided by expected. So your formula would look like this for the first entry, female in brand 1, and then just drag that using the fill handle, and it will replicate the formula for every single combination of brand and gender. Finally, add together all the numbers in the chi-square test table to get your chi-square test statistic value. The bigger this number is, the more likely you are to reject. For the p-value, you use the formula chi-square.test. Here's my counts from my original observed data from the energy drink survey. Then I select the counts from the expected values that I had to calculate. That gives me a p-value of about 4%. 4% is just less than 5%, which is our typical value for alpha. So because 4 is just less than 5%, we reject the null hypothesis. This means there is what's considered a significant difference in energy drink preferences according to the gender of the person. So check your calculations you should have got these values for the expected value, the chi-square test values, your test statistic and p-value. Also check your interpretation and decision. They don't have to be written the exact same as mine, but as long as you have something about difference, or you could have also wrote energy drink preferences depend on gender. That would also work for your interpretation, as long as you have something about them being different or dependent, because we rejected the null hypothesis in this example, whereas in the previous one, oops, wrong sheet. In our previous one on education and gender, we did not reject. So you saw an example of each one, and it gives you an idea of how to interpret the values. These are the steps that will always follow for the chi-square test, this 4-step procedure. If you have any questions, please reach out to your professor, but thank you so much for watching this video, and this is the end of learning outcome 3 for the course.